Welcome back to this second lecture on neural network quantum states. Just as a quick recap of what we saw yesterday during my first lecture. So essentially, I was discussing quite generally. Actually, sorry, I think you cannot see my iPad. Just a second. Okay, sorry. So as I was mentioning, I mean, yesterday we saw some generalities about variational states. So, and specifically, I told you about the fact that we want to parameterize my quantum state with some parameters W, right? So this is, in general, then a linear combination of my basis states K with some coefficients Ck that will depend on these weights or on these parameters W. And I told you that we have mainly, I mean, the two classes of variational states that I discussed yesterday are two. So the first one are those for which I can compute expectation values of some operator of some observable exactly. So exactly, again, in the sense that you only have some possibly rounding error in your computer if you want. And two, this other more general family of states for which you can compute expectation value statistically. Sorry. So in this case, again, yeah, the idea, as I was telling you, is that in this second class of quantum states, which is more general and quite interesting because we can also afford non-local states, so that are not strictly enforcing locality and that can represent therefore also, for example, volume law states. And I told you that you have to satisfy, in this case, two requirements in order to be able to work in practice with these more general states. So the first one is that you are able to compute the amplitudes of these states efficiently over a given vector, over a given basis K, basis element K, and then you're also able to sample from this probability distribution density that is the Born, if you want, the distribution psi of K squared, essentially. Okay, and then if you do that, I told you that you can represent, or you can estimate this expectation value, quantum expectation value, as a statistical expectation value over using some M samples that you've generated of what I introduced to be this local, right, estimator or local observable that somehow is related to the quantum operator. And I gave you the definition, and I told you about some sampling strategies based on mostly based on the Markov chain, so Markov chain Monte Carlo, and I told you how in general that is a Swiss knife approach that you can use for several different, if you want, probability distributions, so, and in particular for wave functions in this case. Then, I mean, we went straight to the idea of using neural network states, so using neural network representations, right, of wave functions, because until that point we didn't discuss how to parameterize quantum states. And in this context, I mean, I already told you a few things, but essentially the main idea was that we have a representation of my wave function, for example, in terms of some nonlinear, you know, deep neural network, which can be written in this form, as we discussed yesterday, where you have an alternating application of linear transformations, or these W weights, and the nonlinear transformation that are these if you want, these G functions that are the nonlinearities that you have. Okay, so this is the typical feed-forward, if you want, neural network. Okay, And then, I mean, you know how to take gradients, for example, of these objects. So using using automatic differentiation, I think that Leigh has told you about this also in the previous talk. Indeed, today, what we are going to do is that we are going to see how we can use all these ideas to indeed do the learning part. So if you want, in the first part of my lectures, I told you about the machine part, which is essentially the representation of the wave function. So you can think that the machine is the wave function. Now we are going to talk about the learning, which is about finding the weights, so optimizing the weights in order to solve some specific task in quantum mechanics. And I will give you a few examples of tasks. So maybe before going there, I would just wanted to connect briefly to what you saw from Juan, actually, during the first lecture, one of the first lectures last week, which is this idea of autoregressive quantum states. Because these are, if you want, the truly, if you want, the computationally efficient states, according to the definition that I gave yesterday. And the reason I'm saying this is that, as I was already mentioning, when you do Markov chain Monte Carlo to sample from this probability density, in general, there's no actual guarantee that the samples are correctly distributed according to your P of K, because there might be some ergodicity problems, there may be some, for example, extremely long correlation times. These are well-known issues in Markov chain Monte Carlo. So strictly speaking, even though in practice, in most cases it works, but strictly speaking, you don't satisfy condition B if you use Markov chain, okay? However, I mean, as we found out in 2019, you can go beyond this Markov chain Monte Carlo approximation, and you can actually do exact sampling. So if you want, this is a way to circumvent, in some cases, Markov chain Monte Carlo and do just direct sampling, okay? And again, as you've seen, so I'm not going too much into the details of this, but the main idea, which is discussed in this paper, Sharir et al. That we wrote in 2019, was published in 2020. So it's a PRL under 24020503. 2020. So the idea is that you write your model, so your wave function, if you want, the coefficients, as a product of some normalized, if you want, coefficient, normalized conditional, so to speak, wave functions. So where this psi I, so this small psi I here that I wrote here, have essentially the form of, I mean, are the complex equivalent, if you want, of a conditional probability. So you've seen in the talk that Juan gave that you can always factorize, if you want, a probability into a product of conditional probabilities, where this psi would be, in that case, probabilities. However, we generalize this construction to wave functions, and you can factorize, if you want, the wave function into a product of conditional, so to speak, wave functions. The main difference now is that this psi in general, both this one and the psi I are complex in general, so they are not strictly speaking probabilities, and they satisfy, if you want, this normalization property. So the sum over all the possible configurations, the possible states sigma of my, if you want, conditional, so to speak, wave functions are normalized in L2 norm. Okay, so in other words, the sum over all sigmas, okay, of this psi I squared is equal to 1. So they are normalized over this variable, the first variable, if you want, to 1. This is a condition that is easy implemented in practice, and you can show that if you implement this condition, then you also for example, using a recurrent neural network, you can also implement this condition, as you've seen in the talk given by Juan. And then you can show that this condition automatically guarantees that the full wave function, so not only the conditional wave functions, but the full, if you want, psi, so the psi of sigma 1 up to sigma n, so the full wave function is normalized to 1. Okay, so this is beautiful in a sense because it allows you to work directly with parametric states that are already normalized, contrary, for example, to a general, let's say, convolutional network or other representation of the wave function. And indeed, then the probability distribution that we are interested in sampling from, again, which is always this one, this psi square, takes the form exactly of again, you see, of the product of conditional probabilities now, actual probabilities, because you will have the square of this psi, right? Okay, so this is, you know, this psi I squared are just conditional now probabilities of spin I conditioned on all the other previous spins according to some order. So you can use the exact sampling techniques that you've seen discussed by Juan during his talk. So essentially you generate the first spin and then you condition the second spin on the value of the first until you generate all the spins without any acceptance or rejection scheme as done in the Markov chain. Okay, so this is exact. There's no approximation. So these are truly, if you want, computational efficient or computationally tractable quantum states according to the definition that I was giving yesterday. Okay. Okay, so this was just also to connect to what you already saw and to also tell you that Markov chain is not the only option. Now, let's see how we can, in practice, learn these weights. Right? So how can we, in general, try to find these weights? I mean, as you know, for example, if we go now to the task of learning the ground state, or learning an approximation of the ground state, if you want. As in all tasks of machine learning, what we do is that we define some loss function, right, that depends on my weights, or the weights of the neural network, for example, or my variational parameters. And it's clear that in the case of the ground state, this loss function is nothing but the energy. Okay, so this is just the variational energy, so the expectation value over my variational state of the Hamiltonian that is given. Okay, now I always put the normalization explicitly because it's not always the case that we work with, for example, autoregressive states that are normalized. Okay, now and again, as I was mentioning, you know, at length yesterday, we can approximate this E of W as 1 over M, right? So the sum over I to M of some of the local energy, so-called. So now the local energy is just, if you want, this local estimator, but for the Hamiltonian. So if you want, we can write it explicitly just to be clear. But this is just, as I was mentioning yesterday, just the sum of K prime of the matrix element now of the Hamiltonian, and then you have psi of K prime divided by psi of K. Okay, so this is just my if you want, an estimation of my Hamiltonian expectation value. So so this is my, if you want, my loss function. Okay, and now what I want to do is that I want to minimize this loss function, and it turns out that not surprisingly maybe, but also the gradients, if you want, of the energy. So if we talk about the gradients of the energy, also the gradients can be written efficiently in terms of expectation values over this distribution. I'm not going to do the full derivation, but you can see it pretty clearly also from this expression. But eventually, if you do the gradients by hand, also taking into account the normalization, again, it's not really a hard calculation, but I will skip the details for now. You can show, I mean, the derivative with respect to the, let's say, parameter P of my energy. Now I'm assuming that the parameters are real, just to be in a simpler case, which is actually pretty general, because even if you have complex parameters, you can always map them to real and imaginary parts that are by definition real. But in any case, so you can show that the gradient is given by twice the real part of these expectation values. So an expectation value of this local energy times of k, so that will depend on the sample that you generated, times an operator that I will call OP of k, the diagonal operator that I call OP of k, that I will define in a moment. Actually, it's a convex conjugate. And then you have another term that comes from the normalization when you do the calculation carefully. So which is the expectation value of the local energy, which if you want is just the expectation value of the Hamiltonian, times the expectation value of this OP operator, that is diagonal, that I will define in a second. So in particular, OP of k, so is defined as the derivative of with respect to parameter p of the logarithm of the wave function. Okay. So these are the kind of things that you need then to estimate the gradients. So you need to be able to compute, if you want, gradients of the log of your wave function. And this typically can be done using automatic differentiation, as you will see tomorrow in the tutorial, or actually this afternoon already. We can use, for example, JAX or any other automatic differentiation tool to compute these gradients automatically for us without having to do the things by hand and efficiently, which is also important. And then, I mean, these expectation values here mean that, again, have exactly the same meaning of this, in the sense that we generate samples from this distribution psi square. And then we average this, again, diagonal operator times another diagonal operator log over this sample of these m samples that we generated, which are exactly the same samples that we have generated also to estimate the expectation value of the Hamiltonian. Okay, so you see that this object takes also the form of a covariance, if you want, between these two operators, which is nice. Okay. Now, so in practice, then the learning algorithm that we have is relatively straightforward in the sense that, as in most machine learning tasks, what you do is that you initialize your weights or your parameters W with some meaningful and not too crazy initial values. Then you sample at each step of this learning. So learning is by itself an iterative optimization procedure that lasts a lot of epochs or several steps, if you want, in normal language. So at each of these steps, you sample from this P of k right. So let's say that I'm at step S. So I will have some weights. So I've initialized my weights W0. So at step 0. And then at step S, in this iterative procedure, I have my weights, my current estimate of the best weights. And from this P of k, which is again psi squared, I will sample some k1 or up to km, so m samples from this distribution. From these samples, I will measure, if you want, I will compute the mean of the local energy, and this will give me an estimate of the if you want, of the Hamiltonian, okay, of the expectation value of the Hamiltonian for that given set of weights. And I can also estimate as I was mentioning, the gradients with respect to some parameter of the energy. Okay, and again, these are written in this form that I just wrote up here. So I'm not writing that again. I will just indicate this as a covariance because it has the structure of a covariance. And then, I mean, what you can do, the simplest thing you can do is that you use your favorite machine learning optimizer, ADAM or SGD or any other optimizer you like, to update your parameters to step S+1. Okay, so the parameter P at step S+1, for example, in the simplest case of the gradient descent, will be given by just minus eta, which is the learning rate, times the gradient of the energy with respect to parameter P. Okay, so and you do this until you converge, hopefully, to some variational minimum for your energy. And you see that, again, as I was mentioning at the very beginning, this procedure does not rely on at variance with, for example, supervised learning. In this procedure, we don't have external data, so we don't have, if you want, I don't know, samples of the wave function or even the exact energies. So what we do is that we generate ourselves our samples with our current model, and then when we improve this model, we generate at each step different samples. So this is crucial here. So at each step, we generate different samples until we self-consistently, if you want, converge to a good approximation, hopefully, of the ground state. Okay. So are there questions about this, or are we good? Okay, so if there are no questions, then I think that we can proceed, and then I will tell you maybe a few words about how we can learn more than ground states. Okay, so until now we've seen a learning procedure that allows you to learn the ground states, because again, this is what we were doing before, minimizing the energy. So how can we learn, for example, dynamics? So this is also an important task that you want to do in quantum mechanics. So you want to learn, for example, so what would you like to do is to solve variationally, in some sense, that I will specify the time dependent Schrödinger equation. So you would like to solve, if you want, the Schrödinger equation, but I mean, you want to solve for psi of t. So let's say that I have my Hamiltonian also depends on time, and you want to solve for this state phi. Okay, so you would like to solve for this state at time t. Okay, so with some initial condition phi 0, which can be relatively simple. So you see that here we cannot use, I mean, for obvious reason, the standard variational principle, because we are dealing with a dynamical problem. Okay, so the standard variational principle. So again, the fact that the energy is the expectation value of the Hamiltonian is larger than the exact energy, cannot be used as it is to solve this time-dependent problem, because we are dealing with an intrinsically dynamic problem, not a ground state. Okay, so how do we do that? So how can we, if you want, transform this task, so the task of finding phi of t, into a learning task? So this is most of the applications that you try to do of NQS are about casting, if you want, quantum mechanical problems into learning tasks. Okay, so the way we do this, it's actually relatively straightforward, and it's based on the idea that we want to have now time-dependent variational states. So specifically, I would like to approximate, if you want, my phi of t, so the solution of the time-dependent Schrödinger equation, with a variational state that depends on some parameters, and I put the time dependency in the parameters. So now I make my W depend on time. Okay, so I have my neural network, for example, with weights that at each time can take different values. Okay, so if you want, the trick here is that I move the time dependence inside the weights, inside the variational parameters. Okay, and I mean, this is a very well-known trick, if you want, that was discovered by Dirac least as far as we know. Which it goes under the name of the time-dependent variational principle by Dirac and Frenkel. So this is essentially as old as quantum mechanics. And the idea is that, geometrically, if you want, is that if I consider now my time evolution, so if I have for example, if I have my state phi of t at time t, okay, which again I'm assuming is parameterized by some variational state with weights that depend on time, w of t. What the correct way of reasoning about the variational principle in this case is geometrical, in the sense that I have to imagine what is going to happen to this state, to this vector, if you want, in the Hilbert space, when I go to time t plus delta t. Okay, so and specifically, what will happen is that my, if you want, my exact state will rotate according to the unitary evolution given by the Hamiltonian, if you want, into some phi of t plus delta t. Okay, so you can think that it's just the exact state rotated after some small time step. But on the other hand, since I'm giving a time dependency to the variational parameters, I have another state, another vector, if you want, which corresponds to my psi with weights w of t plus delta t. Okay. So in other words, you can say I'm changing by some amount all the parameters, okay, and at time t plus delta t, my variational vector, which is just a vector in the space of all possible states, will rotate too, but in general, this rotation will be parameterized by how much I'm changing the variational parameters. So the goal of the variational principle in this case, if you want, is to minimize the angle, or to optimize, if you want, the overlap between these two vectors. So the exact time evolution at time t delta t, and the approximate time evolution that instead is generated by the dynamics of the variational parameters. So you have two different generators, one generated by the Hamiltonian and one generated by the variational parameters. Okay. Maybe it's a good time to, actually no, because we started at 11:30, so now I was confused. No? Then in practice, what does this mean? It means that you have the exact state, if you want, phi of t at the initial step. So this will be my, so I'm assuming that in this scenario that the initial state is already given by some variational state. So if you want, this is my initial condition at time t. Okay, and then as I was mentioning, if you want, geometrically in equations, this means that at time t plus delta t, this exactly evolved state that I'm calling phi as opposed to psi, which is instead the variational state, as you know, will be given by 1 minus I delta t, the action of the Hamiltonian on my phi of t, which was my initial condition. Okay, so plus order of delta t squared. So I just linearized, if you want, the time of e to the minus I delta th, or just rewriting the infinitesimal form of the Schrödinger equation. So this is the exact time evolution, if you want. So this is the blue vector in this picture. However, the approximate time evolution will happen because my, if you want, my weights, my parameters will have some dynamics. Okay, so and what I can you can show, and I will give you an example. I will give you more details in a moment, but you can see that this is equivalent to saying that your variational state has some generator of the dynamics, which is not in general the Hamiltonian. It's another operator delta that I will define in a second, applied on your initial vector, which is in both cases the same. Okay. So what is this the generator of the dynamics, of the variational dynamics in the case of, if you want, of a variational parameterization. Well, the idea is pretty simple, because since I'm assuming that these W's have some some internal dynamics, in order to find the value of delta, or to find what delta is, you can just, for example, compute the amplitudes of my variational state at time t plus delta t. And if you do that, okay, so you will see that, so just linearizing again at first order in time, you will have just the initial state. So this is at time t. So this is psi of w of t, if you want, plus delta t, the sum over the parameters of the derivative with respect to each of the parameters of the amplitude. Okay, sorry, now I don't have enough space, so let me move this down here. This is one of the cool things you're going to do on a blackboard. So, and then you have delta t times w dot. So you have the time derivative, if you want, on my variational parameters. So this is essentially the main idea, okay? And then you have order, higher order in delta t squared. Okay? So you see that if you do this expansion, you clearly see that the amplitudes, if you want, of your state at time t plus delta t will be, if you want, governed by the time derivatives of your variational parameters. Okay, and they are coupled to this, if you want, to this to the gradients of the log. Again, these are the same object essentially as we identified before. So these are just the gradients of the log of the wave function. And indeed, the operator delta that if you want, enters the equation that I wrote above, essentially is related to this this expression here, I mean, and essentially is the sum over p of these operators that here I called O. So these are really the same. So if you want, these are the so these are diagonal operators. So you can write them also in this form if you'd like, but these are just diagonal operators. So these are just these OP times W dot of P, okay, at time t. So this is if you want, your variational operator that is driving the dynamics. It's just this diagonal operator. So in one case you have the Hamiltonian, if you want. In the other case you have these diagonal operators times the gradients, the time derivatives of the variational parameters. That instead is going to change your parameters. So in general, these two operators, of course, delta and H, are different. However, what we do in the context of the variational principle is that we try to match them as much as possible. And matching them means that on one end, then I will have a state A, which will be given by, if you want, the identity 1 minus I delta t H, applied on my initial state phi of t, and in the other case I will have a state B, which is the identity plus delta t, again this diagonal operator that now I'm writing in this form, W dot P. Okay, so I have two states A and B. Matching them means that what I want to do is that I want to maximize the fidelity, okay, between these states, the state A and B. And you see that this fidelity that I write just as the overlap between A and B squared divided by possibly the normalization of A and B. Okay, so you see that this fidelity will depend parametrically on what? It will depend on the only parameters that I've left here, which are not the W themselves, but they are the time derivatives of the W's. Okay. So you see that now the thing that I can try to optimize in order to increase this fidelity as much as possible at each time step are the time derivatives of the W's, not the weights themselves. So that's why there's a shift if you want, in paradigm compared to the static ground state variational principle. In that case, you minimize the W's. Here, you optimize over the time derivatives. So what you do when you maximize, if you want, with respect to these time derivatives of the weights, the fidelity, you will find actually at this order in delta t a quadratic equation actually for in W dot. So in this W, in the time derivatives of the variational parameter. So you will get an equation of motion for W dot P. Okay. So essentially what you do is that you take the gradients, if you want, of FAB with respect to W dot P, you set them to 0, and this will give you an equation of motion for the variational parameter. So in other words, it will give you an equation that these W dots have to satisfy in order to maximize at each step in time the fidelity. Okay, so I hope this is clear. And in practice, the equation of motion that you get, let me write that for you. It's a quadratic, as I was mentioning, is a linear, it's a quadratic problem originally. So when you take the gradient, it becomes a linear, if you want, system that has to be satisfied by your time derivatives. And the equation takes this form. So it's a matrix that I will define in a second, SP prime, sorry. So my parameters are called P times my W's. So again, these are the unknown that I have to solve this equation for. And these have to be equal to OP star, the local energy, so the expectation value again always on the same samples, OP star times the local energy. Okay, so this is slightly similar to to the gradient that we saw in the previous case. There are some differences, and the matrix S that I've introduced here is related to the quantum geometric tensor. Okay, so specifically, if you take real valued parameters, now this SPP prime will be the real part actually of the quantum geometric tensor, which is defined as technically as the gradient of psi with respect to parameter P overlap with the gradient of psi with respect to parameter P prime minus the psi in the WP psi times psi the psi in the WP prime. Okay. So this is a quantity that arises naturally in many contexts, and it's essentially defining the geometry of the variational space. So I don't want to enter too much into the details of this, but it's really a very important quantity because it essentially tells you how close two variational states are. So if you take this as a metric tensor, so this metric induced by this tensor will tell you how close two states are. So if you want, it's the metric that comes from the overlap between two states, okay, and between two variational states. And if you do the calculation carefully, you will find that this is exactly the object that you get here. It's a very important object for many applications. And in practice, how do we estimate this if you want with samples? Well, you can show that this object can be estimated also as the expectation value. So again, this is the real part, just to be clear. The expectation value of this O star, again, these always present operators, diagonal operators that are these variational operators, OP times OP prime minus OP star OP prime. Okay, so again, these expectation values are taken over, as always, over psi squared at some point. So again, so these expectation values means that these are again 1 over m sum over I to the m of my P of K of I that I defined before, with some function which would depend in general on K, on the samples, okay? And in general, since all these operators are diagonal, it's clear what this function is. So we have a way also to estimate quite generally this, the real part of this quantum geometric tensor, in most cases also the imaginary part, but typically we don't need it. Then the way we solve, if you want, variationally, or we try to solve variationally the dynamics, is a fairly simple extension, if you want, of the standard variational Monte Carlo. So this procedure where we learn the weights for the ground state, and this extension that that we call the time-dependent variational Monte Carlo. Variational Monte Carlo, of course, can be applied essentially as it is to neural network quantum states, for example. This is more general and applies to all sorts of quantum states you can work with sampling. I mean, this is the TVMC in short, and it's a method that we introduced before neural networks, but still pretty useful in this paper in 2012, actually. Sorry, was there a question? No, okay, maybe
no.
So.
No, there's
okay.
no.
Okay. So, and this method again is an extension, relatively straightforward extension of this learning algorithm that I wrote here, in the sense that what you do now is that step 0, you have your initial weight W of t equals 0. So you start your, if you want, your Schrödinger equation at time t equals 0, typically from a simple state or from some state that has a known, if you want, the variational representation, and then you try to propagate in time this state. And then at each time, what you do iteratively, now this, again, the learning time, if you want, here is the actual physical time instead of an optimization time as we had before. But so at each step, what you do is that, as before, you sample from your Born distribution density P of K that will be time dependent, simply because I'm at a given time and my weights take different values at each different point in time. Okay, so I have my W of t, and I sample with the usual techniques from this P. And then on these samples, on these M samples, let's say, I measure, okay? So I measure the real part of the quantum geometric tensor, this SPP prime, and I also measure this G of P. I mean, I call the G of P, actually, this object here. Okay. So actually, yeah, I should take also the real part of this object to be consistent if I work with real parameters, as I'm doing now. Okay, so G of P is the real part of this object, but again, it's very similar to the gradient that we were seeing for the ground state minimization, and I can estimate this object again just using the same samples, so psi squared, at each step. So I measure this quantity, I estimate these two quantities, the matrix and the vector. And then what I do, this is the extra step that you didn't have before. If you want, I solve a linear system of equations. Okay, to find these W dots of P. Okay, because you see that the linear system of equations that this W dot satisfies this one that I wrote before. Okay. So now that if you want, I solve this linear system, I find W dots, I can use my favorite linear algebra tool to do that. And then, I mean, in the most simple scenario, what I can do is that I go to time t plus delta t with my updated parameters, which again, updated in this case means just, for example, using a time integrator scheme where I update them with, in the Euler scheme, I would do this simple-minded update where I just send the time t plus delta t, my parameters, to delta t times the time derivative that I just found by inverting, this equation. Okay, so this is then I would go down now at time t plus delta t. I would sample again, measure, and until I go to the final time of my time evolution. Of course, it's strongly advised that you don't use a first order if you want ODE solver, ordinary differential equation solver, as this simple Euler scheme, because this will not be very stable unless you take delta t to be extremely small. So in general, you might want to use higher order integration schemes, for example, Unja-Gutta and others. Okay. So this is what we do to do the dynamics. You will see examples in the tutorials tomorrow, I think. And maybe just a word before going to the break is that this kind of approach can be generalized. I mean, can be done also not only in real time but also in imaginary time. So what does this mean? I mean, maybe you are familiar or maybe you are not familiar with imaginary time evolution. But I mean, the main difference of imaginary time that I'm calling here tau as opposed to t, which is the real time, is that I assume that my imaginary time evolved states of phi of tau now it will be given by the exponential of minus tau h applied on some initial state phi 0. Okay, as opposed to, again, as before, if you want the exact evolution in real time, which has a minus I th, if you want, if my Hamiltonian is time independent, phi 0. Okay, so you see that there's this formal difference in the exponent, which is very important because this time evolution here is unitary and this one is not. Okay, but so why are we interested in doing imaginary time evolution? Well, the reason is that you can show pretty easily, I'm not going to do that, that in the limit of infinitely long time evolution, imaginary time evolution, phi of tau converges to the exact ground state of the Hamiltonian H. Okay, so this is the exact ground state of H. Okay, you can show this in a few lines of calculation. So this is the only condition if psi 0, so the exact ground state, is non-orthogonal to the initial state. Okay, so if you satisfy that your initial state, if you want the phi 0 for this time evolution, is sufficiently non-orthogonal to the exact state, take a mean field, which might be bad, but typically not necessarily orthogonal to the exact ground state, then if you are able to follow this imaginary time evolution, this will lead you actually exponentially fast in the gap with the first excited state to the ground state of your Hamiltonian. Okay, and I mean you can. So how do we solve for this imaginary time evolution? I mean, it's formally essentially almost the same as what we were doing here. The only difference is that if you consider this state here, instead of having an I that came from the fact that we are doing imaginary time evolution, here you will have a minus delta th. So this is the, if you want, the only difference. So the I will drop from this equation. So the net difference is then, if you want to do imaginary time evolution, you have to solve a linear system of equations, which is very similar to what we did before. Now, W dot means the derivative not in real time, but in imaginary time. It's the same of this. Again, the real part of this object here. So this OP star of the local energy minus the expectation value of the local energy. Times OP star. Okay. So if you see the formal difference with respect to this case is that here essentially we had an I and the minus of difference here. But I mean, it's almost the same with of course, the very important difference is that these variational dynamics will follow the non-unitary imagined time evolution. Instead, when you put an I here and a minus here, you will get a variational approximation of the real-time evolution. And this approach is completely equivalent to what is known in literature as the stochastic reconfiguration approach. So following the imaginary time evolution variationally is what is known in literature as the stochastic reconfiguration. I mean, in the context of, again, of variational Monte Carlo, which was introduced by Sandro Sorel in the late 90s. And I mean, this is nicely explained in the book, which is that I pointed you to at the beginning, which is called this Quantum Monte Carlo book that I had in the list of references that I enclosed in the first lecture. And actually, incidentally, this is very close to a method that was discovered in machine learning, which is known the natural gradient method. Natural gradient descent that was invented by Amari in the context of unsupervised machine learning, essentially, so not quantum mechanics. So the only difference being that in the classical case, if you want, this matrix is, I mean, is not the real part of a complex object, but it's actually real by construction, and it's the Fisher information matrix that is associated with your model when you try to minimize a KL divergence. I mean, you can look at the details of this in the paper by Amari, or just look at natural gradient, and you will see. But the idea is always essentially the same, and essentially you have a positive definite matrix. This is positive definite. I mean, you can convince yourself also by looking at the form. So this is just if you want, a covariance matrix. So it is positive definite by construction. Yeah, you see it here. Actually, it's a covariance matrix. So it's positive definite. And then what you do is that you, if you want, you precondition when you solve the system, you multiply this object, which is essentially the gradient of the energy, with the inverse of this positive definite matrix. So you can also, another way of looking at these updates is thinking that this matrix S is just a preconditioner for your gradients that will speed up, if you want, convergence towards the ground state. And indeed, I mean, it turns out that this approach, so the idea of using imaginary time evolution to find the ground state, is extremely powerful for neural network quantum states, and in most state-of-the-art applications, it is what really gives you the most accurate energies, rather than simple gradient descent using Adam or any equivalent. Okay, so this is also an important connection and something that you should be aware of. So I think that now I will do my 15 minutes break, then we can reconvene maybe at 12:45 to discuss my final part. Okay, thank you.
Yeah, that's perfect. Does anyone have any questions right now before the break? Over there. Wait, my microphone is working.
It's a question about the previous part, the stationary one. I'm not very familiar with quantum Monte Carlo, but can you kind of compare the algorithm that you were describing to do the ground state approximation with the neural network states with a quantum Monte Carlo approach?
Yes. So right. So the quantum Monte Carlo is a large family of techniques. So maybe you have in mind, I don't know, path integral Monte Carlo, or yeah, actually, what do you have in mind exactly? What quantum Monte Carlo do you have in mind? Maybe path integral Monte Carlo, or?
I mean, like I said, I'm not very familiar with.
Okay. Sorry. No, okay. I thought. Sorry. Okay. All right. Okay. So okay. So in general, these path integral Monte Carlo approaches or some quantum Monte Carlo approaches are based on mapping the quantum problem onto an equivalent classical problems. For example, using the path integral formulation of quantum mechanics. And in that case, what happens is that this mapping is always valid, but can be interpreted in terms of sampling, so in terms of stochastic processes, only in the absence of what is called the infamous sign problem. So the sign problem happens when, for example, you typically have fermions or frustrated spins. And in these cases, this mapping, I mean, you need to introduce some extra approximations when you do the quantum Monte Carlo. So it is not exact anymore as before. So here, instead, we don't have same problem, but we have the approximation that comes from the wave function, so the fact that we have a neural network. So what we can do is that we can compare ground state energies. Strictly speaking, for example, when we want to benchmark our neural networks to quantum Monte Carlo results without same problem. So this is something that we've done and we do routinely. So in that case, yeah, as I will show you also later, we find a very good agreement with the exact, if you want, the results that are available without same problem. However, the important point is that we can go beyond that. So we can do cases that have same problem. And those, strictly speaking, cannot be directly compared. I mean, not at least with the standard path integral Monte Carlo, because the path integral essentially breaks down on even relatively small systems because of this same problem. So the direct comparison can be done essentially only on the same problem free models. And on those, yeah, we see typically a very, very good agreement with these neural networks. So, but just to give you an idea, if you try to solve the dynamics, for example, with path integral, you can't essentially. Yeah.
Thanks.
There's one more question, two more questions.
Hi, I have one question. So this neural network representation, does it preserve some kind of structure of the Hilbert space that you can add to neural network representations? Or maybe I'm not understanding something fully, but can you add to such a states in your neural network approach?
So, sorry, structure of the Hilbert space, can you clarify what you mean?
So my question is, if I construct two wave functions with the neural network representation, can I add them, for example?
Can I add them? So
yes, add one to.
So if you see, okay. So you say I have a neural network A,
yes,
neural network B. Can I obtain a neural network C as the sum of A and B?
Exactly. Yeah.
So the answer is I wish I could exactly, because if I could do that, you would essentially show that you can simulate all quantum computing classically efficiently. But this is unlikely. So actually, no, we don't have a way to do that in general, unless you do an approximation. Actually, I will say something about this later on. Yeah. So we can do that in specific cases, but in general, no, it's fundamentally hard. Yeah.
Okay, one more question.
I want to ask, when do you use stochastic reconfiguration instead of like just minimizing the energy? What are like other systems where like it's better to minimize the energy and systems where it's better to use stochastic reconfiguration, or one is better than the other always?
Well, I mean, in our experience, stochastic reconfiguration is always performing better typically than the standard gradient descent. Of course, I mean, you have to factor in that this approach is more expensive because, I mean, even though, as Filippo will tell you, we don't really store these metrics in full because it would be too expensive. So we have a way that still scales linearly with the number of parameters. nominally, but still this as a prefactor is more expensive than the standard gradient descent. So it really depends on how much time and space you want to invest in this optimization. But if you want some enough time and space, this will give you that extra mile in terms of energy and accuracy that you cannot get with standard gradient descent.
Okay, thank you.
So if you want to get to 10 to the minus 6 or 7 accuracy in the energy with gradient descent, I would say it's much harder, yes.
Okay, any more questions? So should we reconvene in 10 minutes? That's roughly 10 to 12. Is this okay for you, Giuseppe?
Okay, good. Okay.
Okay. So Giuseppe, are you here?
I am, yeah.
Okay, people are coming back. Okay, welcome to second part of neural network quantum states.
Okay. So yeah, welcome back. So I was discussing how we do imaginary time and real time evolution using a variational principle. And so far we've discussed essentially 2-3 tasks that we can solve variationally. So one is finding the ground state. The other one, so if you want the static time-dependent independent Schrödinger equation. The second task was solving variationally the real-time time evolution, so the time-dependent Schrödinger equation. And the third task, which, however, is related to both the previous two, which is doing imaginary time evolution. And in all these cases, I mean, there is a natural, if you want, loss function that you have to identify. So in the case of ground state, it's just the energy. In the case of time evolution, it's not the energy, but it's this overlap essentially at each step. Okay, or the infidelity, if you want. That's the thing that you minimize. Now, there are other tasks that are not necessarily driven by data. By the way, there are also many other tasks that I didn't discuss today. So, for example, you can do compute finite temperature properties. You can so you can use, for example, density matrices. This is some important work that Filippo did, for example, with there in Warsaw. So you can ask him if you have questions. So you can do Lindblad, so dissipative time evolution, and you can simulate circuits, as I will show you later. So there are many tasks that you can solve by defining a suitable loss function that you then minimize with these optimization machine learning approaches. And all of these tasks, including, again, also finite temperature, for example, do not require external data. So this is the only data that you need if you want is the Hamiltonian. So you just need to know what is the Hamiltonian of the system. However, there are other tasks that need data, so they are different. And I wanted to just maybe briefly mention, if you want, this approach, which is so this task where you try to learn from experiments. So what do I mean by learning neural network quantum states from experiments? So I mean that imagine, for example, that you have let's say an ideal quantum system. So you have a quantum computer, for example, so a closed quantum system, ideally. And what you can do is that, essentially the only, one of the only few classical operations that you can do on this device is that you can measure the system, right? So what you can do is that you can perform a projective measurement. And in general, for example, if I have some computational basis, so again, imagine that I have spins, for example, I can certainly, this is one of the, if you want, one of the postulates of quantum mechanics, then the probability Q of K of measuring a certain set of quantum numbers, as you know from the postulates, is given by the overlap of phi, so the wave function, if you want, of my quantum computer or my experiment, overlap with k, so my set of quantum numbers squared. So this is just the concept of projective measurement, right? And you know, again, from the very postulates of quantum mechanics. So, for example, imagine that I have a two-dimensional system. So the first time that I take a projective measurement and I have spins, for example, on a lattice, or I have qubits, if you want, I will observe that some are, I don't know, up. So the blue are up, for example, and some of the other spins that I have on this lattice are down, so they are in red. Yeah, so this is not the perfect square lattice as I wanted to do. Now, more or less it is, but so you get the idea. So I get this classical, if you want, snapshot of my quantum system, and the probability of measuring, for example, this up, down, down, up, etc. configuration is exactly given by the Born rule. So this probability. And then I do again, if you want, I re-prepare again my system from scratch. I re-prepare the same phi, because these projective measurements, as you know, are destructive. So, and I can, for example, measure again my spins, and I will find another setting, another arrangements for the spins. Degrees of freedom. So some of those will be up, some will be up, down, and again with some probability. And the probability that this happens is again given by psi squared. So this would be my K1, K2. Okay, so I have, I don't know, Km measurements that I performed in this basis of my wave function. Now, what is the goal then? So the goal now, if you want, in my neural network approach, is to reconstruct. So it's not to find the ground states of anything, because you know, in principle, I don't have any Hamiltonian here. I just have a wave function. So the goal is to reconstruct, if you want, the wave function. So in other words, the wave function amplitudes of my wave function in some fixed computational basis K, using only, if you want, these projective measurements. So these projective measurements. Okay, so this task is known as a quantum state reconstruction. And it's important, for example, if you want to certify that your state, the state that you've generated in the system is exactly what you expect, or to be able to measure some quantities maybe more efficiently than you can do on the hardware. There are many reasons why you might want to, for example, to be able to reconstruct, or to have a classical, if you want, reconstruction of these wave function amplitudes from the data that you have in the experiment. So the question then that we have to address now is, what is the, if you want, the variational principle, or something that we can use to do this task. Okay. So is there some equivalent variational principle that we can use? And there is, as it turns out. So the idea is that what I can try to do, I mean, my main goal is that I will try to reproduce, if you want, to have a model for my experimental state, again, trying to approximate this with a neural network quantum states, for example, that will depend on some weights W. Okay. So if you want now, my task will be to find the weights W that best approximate the experimental state that I have access to. Through measurements. Okay. So, and if you look at this, then now in terms of having a model, which is your model wave function with some parameters W, then what happens is that if you perform a measurement, projective measurement, I mean, conceptually on your variational state, then of course the probability of measuring a certain K will be given by the same rule for some W weights W, which is again the same P that we were discussing when doing the ground state optimization. Right, so this is the probability of observing a certain quantum state, a certain, if you want, quantum number K, on the variational ansatz. And on the other hand, I mean, as I told you before, we have the exact, if you want, projective measurements probability distribution that we don't know explicitly. We only have samples from it, which is this Q of K. Okay, so you see that I have on one hand a probability distribution density that I can compute for an arbitrary K, because we satisfy again the postulates that we had before. And on the other hand, I have the exact, so this is approximate, this is exact, but the exact is not something I can query for an arbitrary K. The only thing I can do is that I can generate samples from this distribution, okay? So this is a standard, if you want, unsupervised learning setting. Unsupervised learning, where, again, as in standard learning task, in standard machine learning, I have samples from this distribution from Q, and I want to approximate this Q with an explicit distribution, with a model that I have, and I want to try to reproduce essentially the observations that I've done from my experimental Q. And the variational principle in this case is minimizing the KL, so the Kullback-Leibler divergence that you've already seen, I guess, between these two distributions of P and Q. Okay, so the definition is just so the sum over Q of K, which is my exact probability distribution, log of Q of K minus the log of P of K, which is my approximate object. And you see that this DKL, so this pseudo distance between these two probabilities, depends parametrically on the weights, because again, this P now depends on W, okay? And we know that this DKL is equal to 0 only if these two probabilities are identical, okay? So you know that if P is equal to Q, so these two probabilities are equal, then the DKL is equal to 0. Otherwise, in general, this pseudo distance is greater or equal than 0, so it's positive definite. So if you minimize it, you can find the best approximation, if you want, that matches the experimental Q of K. So we want to now if you want my loss function as a function of the weights is just this distance of pseudo distance DKL, and I want to minimize this loss function. Okay. Why do we use the KL divergence? Because the gradients of this divergence are nicely expressed in terms of quantities that I can measure in practice. This is one of the main reasons. So, for example, if you compute the gradient of this KL distance with respect to parameter WP, so you will find that it's given by the expectation value of so the derivative with respect to parameter P of the log of so f of K. I will tell in a moment what f is, because I realized I didn't introduce it, over my model distribution P minus the derivative with respect to parameter P of the same quantity f of K, but computed over the experimental distribution Q. So what is f? It's simply the fact that, so essentially I'm taking my P of K, so in general to be an unnormalized distribution. So I will take this to be Fk of W divided by some normalization N of W. Okay, so if you want, F is just the unnormalized probability density, because in general I might work with probability densities that are not normalized. But if the probability is normalized, you don't have to care about this distinction between F and P. But in any case, I mean, you see that again, I have exactly what, or something similar that to what we were discussing before, because now if you think that I've parameterized my wave function psi, right, in terms of a neural network, then this log f is nothing but the log essentially of my wave function. So actually the derivative with respect to parameter p of the log of f of k is essentially equal to twice this operator again op that we defined before. Okay, so if you have your model wave function, you can compute again these log derivatives these enter in all applications, and they also enter in this problem of minimizing the KL. And the reason why this gradient is easy to measure is because you can estimate this by just drawing again samples over from your distribution P, which is again samples from psi square, and we know how to do that by now. And this by instead using the sample that you have from the data. So this is the important difference with respect to the previous application. Now our gradient will feature also a term that comes from really the data, and then we have to take this into account. Okay.
Giuseppe, there's
Yeah.
2 questions.
Yes, please.
Is the KL divergence easier to minimize than, for example, the fidelity?
Yes, absolutely, because the fidelity is not something we can estimate. Whose gradients can be estimated efficiently without knowing the value of the wave function. So the main problem is that we don't know phi of k. Otherwise, we would have already solved the problem. The only thing that we know are samples from phi of k squared. Okay. So, and in this sense, if you want to try to minimize the fidelity, so to maximize the fidelity, you can convince yourself that you in any case, to estimate its gradient, you need to know the value of phi of k that we don't know. So the KL is really the only thing, or essentially the only thing we can do. Yeah.
Another question?
Hi. So if we go back to the KL divergence, it doesn't seem like that it's symmetric between P and Q.
It's not, yeah. Mm-hmm.
Does it matter when we're doing the optimization, which order we choose?
Well, it matters in the sense that you should always take Q here, otherwise you will have issues with the gradients, I think. Yes, so that's what the commonly adopted choice, because this is the choice that allows you to have a simple to measure gradient essentially. Yeah. But again, that's why I was saying this is not a distance in the sense that it's not symmetric, and it is one of the reasons. But it has the property still that it's zero. It's positive. I mean, it's a positive object that is zero only when the two are equal. So you can still use it as a proxy if you want to the actual distance. Yeah.
Okay, thank you.
Okay. So yeah. So the thing that I wanted to add right now is that, I mean, until now I've cheated a little bit, because if you do this operation, the only thing that you can reconstruct if you want is a psi squared, right? In the sense that the measurements that we have here give us really information only about psi squared, phi squared, so the exact. So this will not give you any information about the phase, if you want, of the wave function, right? So if you want to have information also about the phase of the wave function, you have to do a slightly slightly more complicated thing, which is measuring in other bases, measuring in more bases. Okay, so the idea is that instead of measuring only in one basis, computational basis k, now we will have many probability distributions QB, if you want, of k, which correspond to measuring in basis, if you want, given by a unitary rotation of UB. Okay, so if you want, what I'm saying is that I'm considering a unitary U that does some rotation in my system, just changes, if you want, the computational basis. And then this is applied onto the original state, if you want, or alternatively, you can think that this U is applied on phi and then you measure in the same basis. That's in practice what you do actually when you work with, for example, with quantum computers. And then since you have this unitary in the middle, now these probabilities, the samples from these probabilities, if you pick several B's here, will also carry information about the phase of the wave function phi, and not only its square amplitude, if you want. Okay, so the difference now, what you do in practice then in this case, is that you define a KL divergence, which is now not only the sum over all the samples, but also the sum over all, or actually the basis that you consider. So there's a sum over K and B of this Q of B and K of the log now of QB of K minus log of PB of K. Okay, where I've defined my model, if you want, the distribution in this new basis simply as the application of this unitary U onto my variational state psi. Okay, with some normalization that I'm writing. And you can show that this is efficient. So, I mean, we can do this in general if this UB is a local rotation. Local, sorry, if you want, K local rotation, okay? So in the sense that it involves only a number of qubits or a number of spins or whatever you have that is non-extensive, okay? So in this case, we can perform this task, if you want. We can compute this PB of K that we need to perform this minimization efficiently. Okay, so if you want more details about how we perform this task in practice, how we optimize things, you can have a look at our paper, which is by Giacomo Torlai and others, which is a Nature Physics 14447 2018. Okay. So this is the paper where you can find more details about this quantum state reconstruction task using neural networks. Okay, this has been used also on experiment. Okay, yeah.
There's another question.
Hi, Giuseppe. So I think I missed the motivation of measuring in more bases. So practically, it would be better to have more samples in a single basis, or?
No. So the motivation is that if you measure only in one sample, right? So you see, sorry, only in one basis. So you see that the probability Q of K is independent on the phase of this function, of this wave function phi. So this wave function phi might have an arbitrary phase that you don't, that is not reflected in Q because there's a square, you see. So what I'm saying is that wave function with different phases will, no, I'm not talking about the global phases. I'm really talking about the K-dependent phase, if you want, of the wave function. Will have the same probability distribution Q. So you will not have any way of reconstructing if you want. So what I'm saying is that if phi of K, you can think of phi of K as the modulus, if you want, of phi of K times e to the I theta of K, right? So what I'm saying is that there is no way of reconstructing theta knowing only samples from Q, because these are invariant with respect to theta. You see what I mean?
Okay, yeah, thanks.
So if you do that instead in other basis, you essentially exploit interference, that and the other basis will give you information about theta. Okay. Okay, so if there are no more questions, then maybe I will, in the last 15 minutes, I will just flash a few applications, or just just to show you a little bit the state of the art in some practical cases, if that's okay for you. Okay. So so maybe I will go to here, Keynote. You can see it. Yes. So right. So one of the main, I would say, playgrounds that have been used to assess the quality of these neural network states for ground states are frustrated spins. Okay, so frustrated spins are family of models. So for example, the J1, J2 model is one of these frustrated models, where essentially you cannot perform quantum Monte Carlo, for example, because you have sign problem, and you can show that in general, essentially everything will we will break in this case. Okay, so you will have a strong sign problem. You cannot find the ground state exact. And because of the same problem, you cannot determine the ground state exactly, and there are some open questions in 2D, whether there is a spin liquid or not, and there are many other open questions. So I'm not going into the details of the physics of this model, but just to show you how we can try to solve this with neural networks. So if you consider, for example, the Heisenberg limit. So the Heisenberg limit is the case where you take J2 equal to 0. So you turn off this, the frustration. So in this case, when you only have J1, then this model is still solvable with quantum Monte Carlo without the same problem. So we can take this as a, if you want, as a benchmark. And in the first paper, we were using these very shallow RBM networks that are just, if you want, fully connected networks with only 2 layers. And in this limit, we were obtaining some, this is the error on the ground state energy on the 10x10 cluster, some accuracy of 10 to the minus 3 or so, okay, you see on the ground state energy by increasing the width of the network. So alpha is the width of the network. This was quite, so can you see my screen, right?
Yes.
Yeah, okay, yes, because okay, so I hope you could see it also before because I had something.
Yeah, it was.
Okay. So you can see that this is the, so did you see the model before? Or did you have a problem with that? Okay, okay, good. So now, so at this point, shallow networks 10 to the minus 3, just to give you a rough idea. Mildly deep networks. So this was one of the first applications we had of convolutional neural networks for quantum states. We had, I don't know, 3 or 4 layers. It was really not so deep, and you could really see that by going slightly deeper, also the improvement in the accuracy would be, you know, tangible. You go to around 10 to the minus 4, and recently, I mean, using this idea of these autoregressive quantum states that I discussed also during my lecture. So again, this is the paper. So essentially, you can show that you can go down here. So it's off charts because it's in the 10 to the minus 5 or so. I mean, on the ground state energy of this model, and this is significantly more accurate than for example, these RBM cases. And on this finite cluster case, this is the state of the art, I think, in terms of precision on this model, if you consider variational approaches. So you see that by going deeper, by using much larger networks, so these had a few 100,000 parameters or even more, you can really improve also the accuracy on this model. And again, this was a good benchmark also for these variational techniques. Now, if you turn on the frustration, which is the hard case, the case that you cannot solve with other approaches, so things become also a bit more complicated. I will tell you why in a moment. But as of 2019, so the situation has a bit changed since then, but as of 2019, we found that in most parts of the phase diagram, these NQS had better results. So better means that our energies were lower than other existing variational results, for example, based on the MRG or these other fermionic approaches. So there were a few points, for example, most notably in the middle, where we had where there were issues where our energies were not, if you want, the state of the art. And the origin of the challenge, I mean, if you're interested in understanding also what are the challenges of these states, is essentially that if you have a frustrated phase, and these are strongly frustrated phases here in the middle, it happens that they also have a large so-called sample complexity. So sample complexity means that the number of samples that you need to learn these phases is significantly larger than the number of samples that you need to learn, for example, an ordered phase. So because just to give you a quick glance of the physics, when J2 is 0, you have this ordered phase. So naively speaking, you just need to see if you want this ordered phase once, or I mean, some fluctuations on top of it, but not many states are needed to understand what's going on in this case. However, in this middle intermediate configurations, you really have a competition between different orders, and you need more samples. So the wave function has to see, during the sampling approach, you have to see more, if you want, snapshots of possible states to understand which one has the lowest energy. And this is reflected, for example, in the overlap. So this was shown, for example, in this paper, very nice paper, in the overlap as a function of the number of samples that you pick. So this is the number of samples that you have. And essentially, so this was a slightly different model, sorry, but so in the high frustrated phase, that in this case is for 1, you see that you need many more samples to have a finite overlap than if you are in a non-frustrated phase, which is instead these curves here. So you see that by moving from one regime to the other, you might need even 100 or 1,000 times more samples than here, which is, I think, pretty reasonable. However, I mean, you can try to beat this sample complexity. For example, if you work with symmetries, so symmetries can allow you to reduce by a factor equivalent to the symmetries that you have in the system, the sampling complexity. And so in practice, as a result of several improvements, actually it turns out that even if you use an RBM, but you use maybe in a smarter way symmetries and projections, you can beat essentially all the other approaches on this J1, J2 model. So as of 2021, neural network quantum states are the most accurate wave functions on this J1, J2 model in 2 dimensions on this 10 by 10 lattice or whatever. So this is these results from Nomura and Imada, who are, I think, have been published. Actually, this is just the archive version.
There's
Okay.
another question.
Yeah.
Hi. Quick question. So, how do you take the symmetries into account in the neural networks?
Yeah. So you will see something about this in the presentation given by Filippo. So I will refer to that. There are different ways, but for example, I mean, in the simplest case is to use a CNN, so a convolutional network. This is naturally, intrinsically translational invariant because of how the filters and because of the convolutional properties of, if you want, of these filters. If you translate the inputs, the output will be invariant. So there are generalizations of this idea that can be done for arbitrary groups, and Filippo will tell you something about that. And also, if you have more complicated symmetries, if you have non-abelian symmetries, so for example, SU2 symmetry, the situation is much more complicated. I don't want to enter in how to do that because it's also a matter of research. But there are tricks to do that. For example, you can work with the representatives of these symmetries with the IREPs and some clever representations. But it's mostly about representations. Yeah. Okay, now, yeah, talking about symmetries, yeah, I just wanted to also maybe give a word about fermions, because that's maybe one of the most important symmetries you can think of. And so fermions, there are, again, many ways of doing fermions, actually. I don't want to tell about all of them. Again, this is also one of the important open problems. So one way of doing fermions is to map fermions back to spins. Okay, so until now we've talked only about spins, and as you know, or possibly know, there is a way to map fermions to spins. For example, doing the Jordan-Wigner mapping. Okay, so the Jordan-Wigner mapping allows you to convert, if you want, raising and lowering operators, fermionic operators, into, if you want, the creation and annihilation operators for spins. So these are sigma plus and sigma minus, just spin operators. The price you have to pay is that you have to introduce these strings, these famous Jordan-Wigner strings, in this representation that correspond to essentially the sign of when you exchange two fermions. Okay, but in practice, so you can always convert a fermionic Hamiltonian into a spin Hamiltonian. The price that you pay is that the Hamiltonian that you have is strongly non-local. Non-local in the sense that you have n-body interactions. So this is highly non-physical, if you want, from the spin point of view, because these interactions can be extremely long range. So these are really not physically, if you want, acceptable interactions. But the mapping is feasible, and you can still use the neural networks that we used to do. There are alternatives, for example, this gravity type mapping, which is quasi-local. I will not tell you about this because we don't have time, but if you want, you can have a look at this paper where we discuss pro and cons of both mappings. But just to give you an idea of the applications, we can use this, for example, to study molecules. So, the prototypical fermionic systems. So, for example, these are diatomic molecules, so carbon and nitrogen. And you can see this is the dissociation energies when you pull apart these carbon atoms or these nitrogen atoms. And these results were obtained precisely by mapping these fermionic systems into in a finite basis onto spin models, and then solving the spin Hamiltonian with simple neural networks. In this case, we were using RBMs, and you can get pretty accurate energies using this representation of the system. Okay. So this is a way of doing these molecules. This is not the only way. Another way is by directly working in continuous space. This is a work that has been done, for example, by Google DeepMind and also another group in Berlin. If you want, I can send you the references later on. So there's really like an explosion of, if you want, neural network applications, neural network quantum states that either work for fermions directly on the lattice as we do, so with discrete degrees of freedom, or in continuous space, an approach that I'm not discussing today, but that it's still essentially the same. The only difference is that your quantum numbers are continuous, so essentially the electronic positions instead of being discrete like for spins. Okay, and then last but not least, there are other applications other than simulating dynamics or simulating ground states. One of my favorite applications is simulating quantum computing. So instead of running, if you want, a quantum circuit on a quantum computer, what we can try to do is that we can try to simulate that same quantum circuit using a neural network. Okay? So the idea is that if I have a quantum circuit which is made up of some gates, so you know that in general I need a universal set of gates. So for example, single qubit rotations, the Hadamard gate, or 2 qubit control 0 rotation. So these three, for example, constitute a complete set of universal gates. Then it turns out, and this also answers maybe one of the questions that I had before, that you can apply these gates, 2 out of these 3 gates, exactly on an NQS, but you cannot apply exactly the Hadamard. So specifically, what you can do is that you can apply exactly, for example, control Z rotation. So if you apply, for example, this rotation onto an RBM, again, just a feed-forward network with 1 layer, you get out another. Sorry, what? Was there a question?
No, there's nothing.
Okay, so you get out after this rotation the same state, the same neural network, the same structure is the same, but with some of the ways that have changed, and you can determine analytically what changes. Okay. The same is true also for control Z rotations. So this is a 2 qubit entangling gate. And you can show that essentially you get out another neural network, but with a slightly larger. So you have to increase one of the hidden dimensions of your units by 1. So it's a small change. And you also can determine exactly what is this weight change that you have to apply. So the only thing that you cannot do exactly, that you have to approximate, is the action of the Hadamard. So the Hadamard, so coming back to the previous question, is exactly the fact that you have 2 states, the sum of 2 states, and you have to approximate the sum of these 2 states with another neural network. So this is the only gate that we have to approximate classically. And then that's what we do as always. So we take, this is the exact state phi that you generate after acting with the Hadamard. So notice that H now is the Hadamard, not the Hamiltonian, but okay, this should be clear from the context. And then what you try to do is that you approximate this phi, so the exact state, with another neural network with parameters theta prime. Okay, so you want to approximate these, and we do that as we were doing with in the case of dynamics. So we minimize the infidelity, so the fidelity between phi and theta prime as a function of theta prime. Okay, so I'm not going too much into the details. You can find them here, but also the gradients of this fidelity in this case can be computed exactly, I mean, using statistical expectation values. And what we showed, for example, recently is that you can simulate relatively large circuits, for example, those that appear in a QoA, so this quantum approximated optimization algorithm that is very popular and has been realized also by Google. Using this approach, you can see again all the details in this paper, but just to show you the final results. So this is, for example, a 54 qubits simulation that we can do again without absolutely no knowledge of the exact result. This belongs to the category of no data, just give me the output. Again, we were able to simulate these circuits with this many gates and 500 gates or so for layers of this QA, using essentially a little bit over more than a workstation with an RDM. And we estimated, for example, this depth, the accuracy that we have on the cost function, which is this C here, is pretty high actually. And at this point, there is much we can compare to in terms of, for example, wave functions, because essentially there aren't techniques that allow you to get the wave function of this circuit with the same precision as the neural network quantum state, as far as we know. So, for example, if you try to simulate the same circuit with an MPS at 54 qubits, we could estimate. We didn't do the simulation because we ran out of memory, but we estimated that the bond dimension that you would need on the MPS is of the order of 10 to the 4 or more, which is significantly hard to achieve in using realistic settings of a simulation even on a supercomputer. And this gets even because the MPS is not done to simulate this family of quantum circuits, okay? Because these are not 1D. And it gives you also an idea of why we can use the neural networks, because these circuits have a lot of entanglement that comes from these entangling gates here, essentially, and we can exploit if you want, the nature of the neural network to encode this long-range entanglement efficiently. Okay, so this was my last point. I don't have time to tell you more, maybe about another application, but so thank you for your attention. And in the next lectures, you will see more applied stuff, if you want, how to put in practice these ideas for maybe also for your problem. Who knows? So thank you.
Thank you very much. Are there any more questions?
Have you studied how, for example, if you consider different quantum circuits that will entangle the wave function, let's say differently, how this can be well represented or not by a neural network state? So as to say, using quantum circuits to study how entanglement can be represented by neural network states.
Sorry, I didn't get the question. Can you maybe repeat? So you want to use a quantum circuit to understand? So can you repeat? Oh, yeah.
So different quantum circuits have different entangling powers, let's say. And so this, did you think about how this could give you information on how well, so if you're able to...
So if I can rephrase, so essentially, we know that there exist circuits that we cannot approximate efficiently. So if you want to rephrase your question. So for example, I mean, if you take the so-called quantum supremacy circuits that Google was running, so those are essentially random states that you generate out of your quantum computer. They have no structure you can truly exploit in order to compress, if you want, the wave function into a classical form like the neural network. So in general, if you have this, random essentially circuits, there is little hope that you can try to compress them. This is a fundamental as saying that you cannot compress random information essentially, right? So for those cases, we know already that most likely our approach will not work. But my point is that for useful applications of quantum computers, the output circuit is not random, should not be random. Okay, so in that case, most likely we can, not always, but we can find often some approximations that are reasonable. Yeah.
Thanks.
Someone else? Oh, it looks like there are no more questions. So let's thank Giuseppe again.
Thank you very much, and thank you to all the organizers. It was really, looks like a very nice school.
Yeah, it's great to have you here. Thanks.
Thank you. Bye-bye.
Bye.
And so now we go for lunch outside.